All right. So the recording for today's session has begun. So once again, welcome to the attendees and to those who are listening to the recorded version. I am Jyotishwaran, a PhD student from the Department of Electronics and Communication Engineering, IIT Roorkee. And this is our third weekly discussion session for the Physics of the Nanoscale Devices NPTEL course. So, in today's discussion session, we shall be uh, primarily dealing with any questions or queries that you might have from whatever has been covered thus far in the course. And as part of our own discussion, we shall be discussing the contents of week 4, the assignment of which is due in 4 more days on the 22nd, if I'm correct. So, yeah, as before, let me start off by asking if the people attending today's session have any questions or queries. Please feel free to ask them. You can unmute yourself and freely ask any questions that you might have.
Hello, sir.
Yes. Hello, Kamal.
Yeah, sir, I go through the week 3 lectures and
Uh-huh.
completed it.
Mm-hmm.
And while attending the session, I found out that sir calculated the DOS for 3D, 1D, 2D, and 0D systems. So
Yes.
basically, he got for 2D system the constant, like constant
Yes.
value in
Yes.
the DOS. So while analyzing the graph of conduction band and valence band, it's a constant value we'll get.
Mm-hmm.
So sir, is there any like different solution to tell why exactly we are getting constant value for only 2D system as compared to 0D, 1D and 3D? Because in case
Mm-hmm.
of 3D we are getting density of state proportional to the square root of energy
Mm-hmm.
like that, and for case of 1D we are getting inversely proportional to energy. But
Yes.
why only for graphene system or graphene or for 2D we are getting the constant value? And if we are getting the constant value,
Mm-hmm.
then is it good or is it bad for our system like that?
Okay. All right. So let us try to answer. There were a number of questions in what you had asked. So let us quickly go through this and try to see try to answer these questions one by one. So
Sure, sir, sure.
yeah.
Then
So
whatever you want to tell, then after that we'll discuss it.
yeah. So now essentially your question is about the 2D density of states.
Yes, sir.
Okay. So, can you tell me what the expression for G to D of E is? You can go through your notes or slides or whatever you have. And yeah, I mean, other people are also welcome to answer.
So for 3D, GE is equal to M star.
No, I'm asking for 2D. I mean,
Okay.
the question was for 2D, right?
Yes, sir.
Mm-hmm.
GE for 2D is equal to M upon pi
Mm-hmm.
reduced Planck constant square.
So yeah, M upon pi h bar squared. So this is, yeah, let me just make this a bit tighter. Yeah, you're correct. That is the expression for the density of states. Okay, so m upon
Yes.
pi h bar squared. Now,
Yeah. Hmm.
I suppose you are familiar with the derivation. It
Yes, sir.
was covered as a
For
part of the lecture. So I am not going to walk through
yes,
the
sir.
derivations again. However, I will point out certain things. So if you remember, from our last week's discussion session, you might have noticed that, I mean, you might remember that we did a derivation for the 1D density of states, correct?
Yes, sir.
Yeah. So let me just share my screen and then we can get started. Uh,
Yes, sir. Actually, I go through the derivation now. It is like same like 3D, 1D, 0D. Just
yes.
my question is like that here we are getting some constant value. So if suppose if we are going through the nanoscale devices, then is it good that this constant
Yes,
value
yes.
or yeah?
So first, in order to understand the density of states, it is good to generally start with the expression for energy of an electron in a system. So this is, oops, the general expression for the energy, more precisely the kinetic energy of an electron in a 2D system, correct?
Yes, sir.
Yeah. So, I mean, this is kind of where we start. Yeah, first, can everybody see the whiteboard? Hello. Yeah, can you guys see the whiteboard?
Yes, sir.
Yeah, oh, thank you. Wonderful. So this is the expression for the energy. Now you can ask, like, where does this, energy dependence of density of states comes from? Just one second. Yeah, please. So, as like you might know from the lectures and as we had also discussed in the previous week, when I write the density of states as g of e, this is nothing but the number of energy states. Oops. Yeah, energy states. Yeah, let us be more precise. So in general, what we do is we write it as GEDE, and we say that is equal to the number of energy states in the range E to E plus DE. So this is the mathematical definition. So essentially what it says is if I have a particular energy value for a given physical system, then how many energy states do I have for that given energy value? So, if you remember from our previous week's discussion, when we did the 1D density of states derivation, like the approach that we followed, we essentially tried to calculate the number of energy states with energy less than or equal to E. Kamal was definitely there for that session. So, do you remember that?
Yes, sir. Actually, you told some different way of calculating the
Yes.
DOS.
Yeah.
Yeah.
So essentially, what we do is we start with the quantity n of e, which is equal to number of energy states. Energy states. Yeah, here I was supposed to write with energy. With energy less than or equal to E. So this is N of E, and yeah, so is there any network issue? No, no issues. Yes. So, oh, sorry. Yeah. So this is the quantity N of E, and when I write the density of states G of E, it is related to N of E by d N of E by dE. It is essentially the derivative of this function N of E. So what happens is this: when we have a system with a particular energy, so now this is energy for a 2D system. Okay. Now, what is the energy for a 1D system? Let us have this over here, but let us have a different expression. So, E1D, on the other hand, will be h bar squared kx squared. Since we are doing kx and ky, let us use that by 2n. Is this okay? Any issues with this statement? Please feel free to voice any queries or concerns that you might have. Is this okay?
Yes, sir, it's okay, but one
Uh-huh.
concept na sir, effective mass.
Yes. Okay. So let us. I mean, since you said effective mass, yeah, that is something sadly that we have not discussed so far because of our week one, week two misalignment. But as I mentioned before, when the time comes, we shall discuss it again. So that will be probably
Yeah.
around week 6 or 7. So at that time, I will revisit effective masses. And until
Yes, sir.
then, you'll also not be encountering the concept of effective mass. So, yes, all of these masses that we write here are effective masses. They are M star. So, now is it correct? Or is there anything else missing? Yeah. Kamal, are these expressions okay?
Yes, sir.
Yeah, okay, good. Yeah, I was waiting for some kind of a response. All right. So, continuing. So, here, what we can notice is if I give for the 1D case, for each value of energy, there is, a unique value of K. So, because of this relation, what we can infer is for each value of E, there is a, or rather, it's actually there is a unique. Yes, there is a unique uh, uh, kx. Okay. And what is kx? Kx is the quantity that we use to label the energy state. So since there exists only one label for a given energy value, that implies there is only one energy state for a given value of energy. So when we use this to calculate the notion of the density of states, we will get a certain expression. But consider the 2D case. So let me drag this all the way down here and let me close this box out. Okay. So let us now, if we consider the 2D case, what happens is for any given value of E, how many values of kx and ky exist? Can someone tell me? Like, is there a unique value or are there more
Sir,
than
2.
one values? Huh?
Sir, 2.
Just two. What are the two values, Creighton? Like, please, can you tell me? Okay, so since there seems to be some confusion, let me give the answer. See, in general, like you can observe that from here itself. So if I fix the value of the energy here, then I can take all the constants to this side, and I will have 2m star E by h bar square is equal to kx square plus ky square. Now that is nothing but the equation of a circle. So in general, for a 2D system, we have for any given value of energy, we have more than one combination of kx comma ky. Okay, is that clear?
Yes, sir.
Yeah. So now again, as before, the k values, kx and k values together, like this set, each unique pair of kx and ky identifies one allowed energy state or a wave function. Okay. So when I have multiple such combinations, pairs, yeah, rather than saying combination, I should use the word pairs more than. And in fact, it's more than one. Yeah, more than one pair of something happened with the yes. Okay. Yeah, Lakshmikanta is here. Hello. Uh,
Yes, sir.
yeah. So yes, more than one pair of uh, k values. So we have, and that is given by kx, ky. Okay. So now each of these pairs tells me that there is one allowed energy state. Since I have more than one energy state for a given energy value, in fact, for any given energy value, what does this mean? Like, what does this imply? What does this entire statement imply? Like, what do you say happens when multiple states exist with the same energy? What is that phenomenon known as? Have you guys heard of this word? Can you read my handwriting? Hello.
Voice is clear, sir.
Is your voice is clear? So can you see what I've written here?
Degeneracy.
Yes. So do you know what degeneracy means? Have you encountered the term in the lectures?
Yes, sir.
Yes.
It is a term in semiconductor, degenerate semiconductors.
Yes, that is there, but even before that, you should have encountered the term degeneracy. So, degeneracy
In
essentially
lecture, sir,
means,
it's not.
huh?
In lecture, sir, not listen about this
Okay,
degeneracy.
fine. So, let us say what degeneracy is. So, when, and let me use a different color. So, when I have multiple states with the same energy, that means that there is degeneracy. Okay. So this is
Okay,
like
sir.
the general definition of degeneracy. So this statement, does this also imply degeneracy? This statement here
Yes,
that I've
sir.
written on the right hand side.
Yes, sir. Actually, you told me that for 2D system, we'll draw the circle.
Yes.
So in X
Yes.
and Y axis, Kx, Ky.
So
So
essentially, what you'll
every
have
state
for
is
the 2D
having the same
system,
energy.
yes, exactly. So you will have a kx and a ky, and if you remember from like whatever derivation that was being done there, please pardon my drawing. As I've told before, I'm pretty bad at this. So there is usually this, region with k to k plus dk. So this length is k, and the thickness here is dk. So this is how the derivation must have gone, correct? So
Yes, sir.
all the k values, combinations, points in this region are to be considered when you are calculating the density of states. Whereas when you are doing the 1D system, you only choose one k value. You don't choose multiple k values. So since I'm picking multiple k values, there is degeneracy, which implies for the same energy value, now there are more energy levels, energy states available. So that is essentially what is reflected by the density of states. So because of this, not I mean, yeah, because of this degeneracy that is now introduced into the system, what we will have is like the energy dependencies. So essentially, g of e, yeah, 1D, yes, let me write it this way, is equal to, or rather not equal to, let us not bother with the expressions. I mean, you might have noticed from your assignments and so on and so forth that more often than not, we won't obsess with what the exact density of states expression is. Unless and until it is a particular question. In general, what is more important is you remember these relations. So it is 1 over square root of e, and g2d of e is proportional to,
Constant.
yeah, or rather e to the power 0, which is another way of saying constant. Okay, and g3d of e proportional to
Directly.
e to the
Roti.
power half. Yeah, or since I used the square root symbol before, let us have some uniformity. Uh, Square root of e. Okay, so what does this mean now? Now, so the reason for all of this is fundamentally degeneracy. Okay, so the reason for this distribution is degeneracy due to the dimensionality of the system. Now, tell me, in the case of 3D density of states, or rather, the 3D systems, is the degeneracy higher than 2D or lower than 2D? Like, for the same value of energy, will I have more points or will I have less points? Can you guess?
Sir, more.
Yes. Can
More.
you give a reason why? Can any of you
Sir,
give me a
because
reason
now
why?
we will get 3 points, K,
Exactly.
KY and KZ.
Yes. Very good. So that is the exact reason. Uh, oh wow! So we have a lot more participants. Welcome, Gautam Kumar Jaiswal. Um, so yes. So we have for the 1D system we have no degeneracy because in fact for the 0D system also there is no degeneracy. Like essentially no degeneracy due to dimensionality. Okay, there can be other degeneracies inside the system, we are not talking about that. So no degeneracy due to dimensionality. And so due to dimensionality, and for 2D and 3D we have degeneracy. So that is the reason why the density of states takes degeneracy, yes, spelling mistake. Yeah. So this is the reason why we have these expressions. Now, what does this mean? This might have been discussed in the lectures, but let us go through that once again. And I will use the 1D case to emphasize that even strongly. G of E is proportional to 1 by square root of E. That implies for 1D case, as E increases, what happens to G of E? Can someone tell me?
Yes, sir. Initially, sir, it's higher, then after, then it's decreasing
No,
exponentially.
like essentially what I'm asking is, does if E goes up, what happens to G of E? G of E always goes down. If I'm increasing the value of energy, then the density of states will decrease. Okay. So
Yes, sir.
how can we see this? Remember your particle in a 1D box. Okay. So how are our energy levels? Like if my ground state energy is E naught, what is the first excited state? Come on, this is week one, week two stuff, particularly in a 1D box. And this we also discussed last week. So at least Kamal should be able to answer. And yeah, Lakshmikanta is also here, so he should also be able to answer.
Sir, can you repeat again?
So what is the next energy level? If the ground state energy for a 1D particle in a 1D box or 1D infinite well,
4 times of E naught.
yes, very good. So the second energy level is at 4 E naught. And the third energy level is further up at
9 times of E naught.
9 times.
yes. So n squared.
Mm.
Okay. So as you can see, as the energy increases, the spacing between the energy levels is also increasing. That implies the density, the number of energy states I will find in a given range reduces as my energy increases. So that is what happens in the 1D system because there is actually no degeneracy due to dimensionality. Whereas for my 2D system, as you all might know right now, as E increases, G of E somehow is a constant. This is again due to the fact that now as I'm increasing my energy, somehow more energy states are available for each given energy level, but somehow at each energy level, this increased number is a constant. Okay. And for the 3D case, as again E increases, G of E also increases. So that is why we have the square root of E dependence. So essentially what all of these statements mean is that it is a mathematical way of representing the dimensionality of the system. Since there is greater degeneracy, as you guys rightly mentioned, at a given energy, I will have a lot more state. So as my energy value keeps increasing further and further and further up, I will get more and more and more energies, because now I have 3k values possible in the 3D case. Whereas in the 2D case, somehow, because there are two cases, like the mathematics works out in such a way that the density of state, G of E, is a constant. Now, to answer the last question that Kamal had asked, like what impact does this have on device design, particularly, when one is talking about graphene and other things. So, I mean, that also has more to do with the contents of week 4 and today's discussion. So, before answering that question, let me stop presenting. A general question to all who are in attendance: has someone gone through the lectures for week 4, at least briefly? Anyone?
Yes, sir.
Oh, good. So, to Lakshmikanta, so does the quantity of density of states show up in the week 4 concepts? Like, does it show up anywhere?
In week 4 concept, it is
The lectures?
the lectures were totally dedicated on transport, how the electron travels in a
Yes.
channel, in a mesoscopic channel, and how it is affected by the
Yes.
your density of states actually, where number of electrons is equal
Yeah.
to density of states into Fermi function.
Exactly. So the density of states is now like an important quantity. It will start appearing for the rest of the course. Like it is going to be there whether you like it or not. So, it is better to get acquainted, get used to these expressions, get used to certain more concepts about them, at least the energy dependence, so that you can, do some of the related derivations and, associated numericals, which you will see later on. So, yeah, as Lakshmikanta mentioned, we have like density of states now features heavily when we are looking at the transport model. So, in that sense, what we will essentially have is, so if so to Kamal, in week 4, like if you go through the lectures, the last lecture is dedicated to the concept of modes. Like the concept of modes is introduced in the last lecture. So in case you have not read it, like when you read it, you will come across them. Now, the modes that are available in a channel, I will briefly be discussing what modes are. However, I shall not be doing the full derivations because, again, time is limited for us. But of course, these things are covered in the course. So, I mean, in the lectures, so you don't have to worry about it. Um, so, modes are directly related to the density of states. So there is a very strong relation between the number of like the modes in a mesoscopic channel to the density of states of the channel. So if the channel is a 1D channel, a 2D channel, or a 0D channel, or a 3D channel, we will have different kinds of mode relations. So that in turn will determine what kind of a current voltage relationship it will have, and that in turn will dictate what kind of a conductivity and like essentially that will dictate the device behavior that you will get, and what kind of designs you will have to make to get the desired behavior from a device of that particular kind. So, to answer precisely the question that you asked, like, is it a good thing or a bad thing? It is neither good nor bad. It is what it is. Like, if you're working with 2D materials, then you have these constraints that are associated with the 2D materials. Now, based on this, you will have to, make certain, what to say, like, changes to say build a 2D transistor versus a 3D transistor, which is typically what one studies at the undergrad and early graduate level. So the devices that we study, we assume that the channel, the source, drain, and or the emitter, conductor, emitter, collector, whatever we are looking. I mean, whichever framework of devices we are looking at, all of these are considered to be 3D objects. But now, since we are moving on to down to mesoscopic devices, we shall look at 2D channels. We shall look at 1D channels, where things like from the first week, where notions like quantization and all these things will start playing an important role, and because of that, certain additional features will come in. Now you can use that to your advantage, or you can think of that as a limitation. So that is up to the engineer, up to the person who's designing the device. I hope that answers your questions.
Yes, sir, understand.
Okay. Yeah. So, any more questions from the attendees? You can also, like, if you have any questions from the weeks 1 and 2 also, please feel free to ask them. This is first and foremost a doubt clearing session. So any and all queries that you might have, we shall address, and after that, we shall move on with whatever we want to discuss for the upcoming week. So I suppose there are no more questions. All right, so be it. So we shall have a brief discussion on about the concepts that are going to be covered in that you shall come across in the lectures for week 4, that you'll need to solve the assignment of week 4. So yeah, before that, we will have a short break of 2 minutes. And yeah, as I had mentioned last week, uh, before joining these sessions, I would appreciate it if you guys can at least give a brief, look through of the upcoming week's assignments, so that we can also have some discussions regarding that. Because I would also like to do some things that will help you guys, solve the assignment questions more easily. I cannot explicitly solve the assignments before the deadlines. Like I cannot discuss the assignment questions directly, but I can definitely give you guys some hints, or some other approaches that can help you solve the assignment questions. So it would be advantageous for you if you guys can go through those lectures before joining these sessions. So I will take a short 2 minute break, and I will be back. Please stay on.
Yes, sir.
Yeah, so back, and we can resume. So, yeah, so before starting with today's discussion session, let me quickly, for those of you who have not seen it, let us just, briefly just sweep through the assignment questions. I'm not going to read these questions out or anything. I just want to point out that there are no numericals in this assignment. Like all of the questions have statements, and you're supposed to answer. These are statement type questions, so you're supposed to remember certain things, and just answer the questions as such. You don't have to solve any mathematical formulae or do any evaluations. In short, you don't need a calculator to solve this particular assignment. So our discussions for this week will not contain any numerical problems, because again, it will be more along the line of the assignments. So yeah, with that, let us begin our discussion. Uh, yes. So what we have is carrier transport. So first, a question to all of you guys. So if I want my carriers to move, like what do I need?
Sir, some sort of force or energy.
Force or energy? Like, can you give a better? Yes, both these statements are correct, but can you give a more refined, like, okay, so if I
Sir, a
want to,
battery, a potential.
oh, very good. Yes,
Uh,
so that's
the,
what I was about to ask. So essentially, like when you say force, if I want to move the
Energy pathways,
electrons, huh? Yes.
modes, pathways.
Yeah, pathways. Yes, we are coming to that. We are coming to that. But even before the pathways exist, like if I want to move my carriers, I need to, have the the capacity to move them. Because if I don't have the capacity to move my charge carriers, then it doesn't matter if pathways exist or not. I mean, I hope you understand that. Like I should be able to cause the motion. So
Yes, sir.
when I say that, I mean, when I think that was Kamal who mentioned the force is there. Like, so how do I imagine it? Do I pick each and every electron and try to push them from point A to point B, or do I try to do something different? So essentially, what we need is for transport.
The potential difference.
Yes, exactly. Like yeah, Kamal had also mentioned that. So the first thing that we need is a potential difference. So first we will have to see where this potential difference is occurring and what the potential difference is changing. Okay, so when we are going to model our carrier transport, so this is, yeah, rather than just saying carrier transport, it is better to say follow the lecture title. So this is essentially the general model of carrier transport. So that is what we are discussing today. Again, the discussions here are supposed to be supplemental to the lectures. Like I'm not taking a separate independent set of lectures. This, in addition to the video lectures and the lecture slides, should make your understanding slightly easy and may contain some hints for the assignment questions. So from our basic knowledge, we know that yes, I need to apply some potential difference, usually given by a voltage V, and then yes, as someone mentioned the word modes, but rather than saying modes, let us say, let us think about in more basic terms, even more elementary terms, like even before going to devices and such. I will have to know what the conductance or resistance of my devices. So I need, typically speaking, if I need to send large amounts of current, I will need high conductance. If I need to send small amounts of, or if I need to prevent the passage of current, I need low conductance or high resistance. So there is this concept of conductance and resistance. So now, is there a relation that you guys know in general that combines these two things? Do we know what this is?
Sir, actually board. We are
Oh,
not saying board.
oh. Please tell me that. I mean, I've been, oh, yeah, I stopped presenting. I'm really sorry. Uh, Apologies. Um, Again, like if I start talking and if you see me writing in the screen here, that's why I keep my video on. And if you're not able to see anything, please stop me right there and ask me to share. Yeah, sometimes I forget to do that. Uh, yeah, now you should be able to see that. Yes. So
Yes, sir.
for transport, first thing we know that there is a potential. Then we need to define something called the conductance or a resistance. Combining these two, we typically have relations like the Ohm's law, which says the current, which is generally denoted by I, is equal to what?
V
V
by
upon
R.
R.
Yeah, very good. V upon R. Well done. So now this is a model. Now, where is this model applicable? This is generally applicable for bulk devices. Okay. So now this is classical theory. This has been known, since that time of Ohm. This is like mid 1800s and whatnot. So we know this for over 150 years. Uh, so when we are moving from bulk or yeah, so when we are moving from say bulk devices to nanoscale devices, which is what we are discussing in today's, not today's, in this course in general. What changes? So, bulk devices are typically called macroscopic devices. Sorry. Macroscopic devices, and these are, nanoscopic or mesoscopic is a word that is used, which one of you also used. So these are called mesoscopic devices. So what changes? So over here I have Ohm's law. Hmm. So what are the things I need to consider when I'm dealing with nanoscale devices?
So first concept is mean free path.
Okay. So where does mean free path occur? Mean free path occurs in the Ohm's law side or this side?
In actually, it's a relation, sir, that the channel length is less than the mean free path length. So
Uh-huh.
that case
Yeah.
will come in the nanoscale devices.
Yes. So, all right. So, yes. So, let us, since you mentioned that, and yes, since it is a good point to consider, let us add that. Why not? So, yes, and we have a much more evolved notion of the mean free path. So for macroscopic devices, so let us say that the channel length is given by L, and let us say the mean free path is given by the quantity lambda. So for macroscopic devices, we have L very much greater than lambda. And for mesoscopic devices, we can say that L is of the order of lambda. When I put a single tilde, it means it is approximately, like it is pretty close. It can be lesser than or greater than, but it's comparable to lambda. So, okay, so we have now defined it in terms of the mean free path as well. So what happens? What are the effects that I need to understand here in order to get a relation that is similar to the Ohm's law? Like when I come to the mesoscopic level, what kind of effects start showing up? Any guesses? So essentially what happens here is, first and foremost, we have quantum effects. Okay. Now, why are quantum effects more prominent here and less prominent here? Can somebody give me some kind of an argument? Like for people who have been attending or listening to the previous week's sessions, this was discussed in our very first session. Like what happens in mesoscopic devices that leads to quantum effects? Like what is the reason that leads to the emergence of quantum effects in the channel?
Because of confinement, sir.
Very good. Yes. So because of this, we have short channels, and short channels in whatever dimensions, 0D, 1D, or 2D, implies that there is confinement. And whenever there is confinement, we have quantization. And when there is quantization, we
Discrete.
have discrete energy levels and so on and so forth. And all of those things are summarized when I say quantum effects. So essentially now we need a model of transport that can account for quantum effects. Okay. So that is our only aim at this point. Okay. So that is the only thing that we are trying to do, and that is our chief concern for, in fact, for around half of the course, this will be our primary concern. Essentially, we need to develop a model of transport and apply it to devices such that we are able to take into account the quantum effects that arise due to confinement. There are a number of things that happen. So you shall, I mean, once you listen to the lectures, you will come up, you will understand what those things are. You will know what those things are. I shall be mentioning a few of them here briefly. Okay. So that is the aim of the contents of week 4. So with this set of lectures, we shall be building a general model of carrier transport which accounts for the quantum effects in mesoscopic devices, and this is usually due to short channel lengths that are comparable to the mean free path of the electrons. Quick question. So what is the order of this lambda for an electron? Can someone tell me? Like, can someone tell me what lambda is, approximate value of lambda is? Hello.
Okay. Hello,
In
sir.
micrometers.
Nanometer.
Micrometers.
10
Nanometers.
nanometers, sir.
Good. Yeah. So 10 nanometers is a good approximation. Okay. So yeah, micrometers is actually pretty large. So if you have and as you can see, a micrometer is around 100 times this. So it actually falls in this category. So if you have channel lengths that are to the order of micrometers, it is actually considered to be a bulk device. So that is a very important thing that people are, in fact, I would say it is a very important takeaway message from this course that if I have, say, a 2 centimeter or a 3 centimeter large, bulk resistor that, I'm using in circuit boards and whatnot. The theory of conduction that I use to study a device of that size is more or less valid for, devices that are in the micrometer domain also. However, when I go down to the nanometer range, quantum effects start becoming prevalent. So modern day fabrication technologies. So if someone looks like something like FinFET devices, what are the typical sizes of FinFET devices? Does anyone here know? I mean, I hope you guys know. What
Basically,
is
sir, in
its?
FinFETs, single gate control the more number of fins. They
No,
are
no,
at
that
the
Yes,
nano
is
level.
no, that
5
is all
And
nanometer.
fine. I'm asking what the channel length for FinFET devices are.
okay,
5 nanometer.
Yes.
yes.
So we have multiple modes. So there is a 17 nanometer, there is a 10 nanometer, and we have gone down to 5 nanometer. So even in our existing technology, like technology that is being used right now in devices that are available in the commercial market, we have encountered this mesoscopic effect because lambda is around 10 nanometers and we have actually gone less than lambda already. So, yeah, very well said. So, the theory that we are studying here is very relevant. It is current and it is being, no pun intended. It is, the state of the art technology that is being used for, fabrication of devices. So, this is not just theory. Understanding this theory will be very helpful in understanding modern, device design principles and concepts. All right. So, moving on.
Yes,
Let
sir.
us open a new whiteboard. So now how do we start, going about this general model of transport? So far, like we have covered the basic of quantum mechanics in the lectures. Uh, yeah, quantum mechanics. And after that, using the concepts of quantum mechanics, we have kind of done KP like so in quantum mechanics. I have my 1D potential well, and I have my KP model, and we have our band structure, and then we have effective mass and all of these things. So these essentially we use quantum mechanics to understand what each and every one of these things mean. And later on, again, using concepts of quantum mechanics, we defined what density of states are. So essentially, what are density of states? Density of states gives me number of energy states. That is the moral of the story. Like whatever derivations we do, everything density of states tells me how many energy states I have in my system, how many energy states I have in my channel as a function of energy. And the third thing that was covered, that we have briefly talked about, is the Fermi Dirac distribution. So Direct distribution. So what does so the Fermi direct distribution now, it has a function, the Fermi function, which is f of e, that is equal to 1 over e to the power e minus, let me say, mu by kt or kbt. Tell me what will occur here. Is it a plus or a minus or multiplication, division? What symbol comes here?
Plus.
Plus. Good. Um, if a minus symbol were here, what does that mean? Do you guys know?
Sir, in lectures they told it will go for both Einstein distribution.
Very good. Yes. So that is for a different kind of particles. So Fermi Dirac distribution is essentially statistics of the electron. Now you can ask, why do I need statistics? We need statistics because okay, so this is the Fermi function. So can you tell me what this quantity represents? Can someone tell me that? In fact, let me just make this slightly more readable.
So probability of
Frequency
finding the electron.
Very good. Yes.
at energy E.
Yes. Yeah. Thank you for completing that statement. So E minus mu by kbt. And yes, so this essentially tells me the probability of finding electrons with energy E. In fact, this is a density, like this is also a density function. So technically speaking, if I am writing this statement, I have to say E to E plus dE. Like, sorry, I've run out of room on the board. Let me just make this more compact. Energy values E to E plus dE, and this quantity is given by f of E dE. So if I have to find out the probability of finding an electron in a given range of energies, I have to integrate this particular quantity. So what is mu? Mu is, can someone tell me what mu is? Oh, this must have been covered in last week. In this expression, can someone tell me what mu is?
Fermi energy.
Yes, very good. Fermi energy. Yes, so it is called the Fermi energy, or another name, a name that I actually like is the chemical potential. Did sir mention this in the lectures? This must have been mentioned in the third week lectures. Did he? This name, chemical potential? Yes, no. Can someone please say something? Yes, no, don't remember, didn't listen. Any answer is fine. Yeah, once again, reminder to those who are new, these sessions are like, again, totally voluntary. You guys can, attend, join, and leave as you please. And these do not contribute to your final evaluation in any way. So you just attend these sessions to, get your doubts cleared, and that is that. You will be graded for your assignment performance and, your performance in the examinations, and that is that. So, was this mentioned in the classes?
Yes, I
Sir,
mentioned.
what is the significance of this name?
So we'll come to that. Yeah, I hope to do that in today's discussion. So there is one way of defining this using statistical mechanics, but we will not do that. That is a very a, it is very complicated. B, it is not needed for us. But there is another way of defining this, which we shall immediately see, like not immediately, like see in the next 10 or 15 minutes. That should be telling us what this chemical potential actually means. All right. So, even before we start doing the current or current density, first we will have to look at charge density. Why is that? Can someone tell me? Oops. Can someone tell me why this quantity should be studied before studying the current density? Someone? Anyone? I mean, it's a general question. You can guess any answer. And again, like there are no right or wrong answers. You are free to say anything that comes to your mind.
So current is like flow of electron means charge.
Yes.
So before going for the current density, we'll look how the charge behave in that region.
Yes, kind of, yes. So even before my electrons start moving, I have to find out if electrons exist there at all.
Yes, sir. Right.
Like if my charge density comes out to be zero, then technically speaking, no current can flow potentially. Like I hope you understand that. Like if there are no free, like from your semiconductor physics understanding, if there are no mobile electrons, then will that device or will that material be able to conduct a current? The answer is no. If there are no mobile electrons, then no current will be conducted by that material. So even before we understand what transport is happening, first I will have to figure out like how many electrons I have, or how many charge carriers I have. So for that I need to understand the concept of charge density. Now, in a solid, how are my energy levels divided? In a solid, let me use a different color. So in a solid, what do we have? We have bands, correct?
Yes, sir.
Okay, and so we have bands. Okay, great. So yes. So now, what are bands? Bands can be seen as a collection of energy levels or electronic states. So when I say energy levels, I also mean electronic states. So there is a collection of energy levels. Now, how many energy levels do I have in a band? How do I know that? So if I ask a question from here, if I ask a question, how many energy levels? Can I answer this question? Do we have an answer to this question?
So integration of energy states from E to E plus D.
Yes. So what is that thing known as? We just discussed it. So the answer to this is density of states. This is why we
Yes, sir.
studied density of states. Okay. So in a given band, conduction band or valence band or yes, is someone saying something? No, I hope not. So when we are looking at a given solid or any material, it has a band structure, and since I have a band structure, there are a collection of energy levels. Now, how many energy levels are present? The answer to that is given by the density of states. Now, these are the number of energy states present. Now, typically, like in our understanding of things, what do we have? Like in a semiconductor, we usually have a, these are two bands. So which one is the conduction band? Above or below?
Above, sir.
Sir, above one.
Okay, okay, fine. Where are the electrons in a semiconductor?
For conduction purpose, sir.
No, in a semiconductor in general, where are the electrons? In silicon, say. Where are most of the electrons?
At conduction band.
Most of the electrons are in the conduction band in a semiconductor.
No, sir.
Homo level, sir.
Valence,
Homo.
edge of valence band.
Yeah. So, yes, so that is so yes, someone mentioned HOMO, highest occupied molecular orbital, or highest occupied energy levels, or lowest unoccupied energy levels. Yes, so these are other concepts. These might have been briefly referred to during our previous in the previous lectures of the course, but we shall not go into that. So in general, like you can take this as a fact. I mean, it is true. It is observed that most of the electrons are in the valence band. Now, in so if I'm considering, let me add another word, intrinsic semiconductor. What does intrinsic semiconductor mean?
Undoped
Yes,
semiconductor.
undoped. So it is just pure material. It is just pure silicon or pure germanium or whatever other material one can think of. And so this particular thing is the band gap. So in general, by default, all the, you know, rather than asking where are most of the electrons or things like that, let me ask a more precise question. At T equal to 0, at 0 Kelvin, where are the electrons?
At valence band.
Yes, all the electrons are in the valence band. The conduction band is completely empty for silicon. Okay, so here we are considering silicon, for example. Okay, for example. So at t equal to 0, all the electrons are here. Only, I mean, none of the electrons are here. So at some finite temperature, some of the electrons will come up here because they get thermally excited. Now, how many electrons come up here? How do I know that? What do I use to find? So tell me this. At a finite temperature, what is like, how does the electron move from the valence band to the conduction band? Is it deterministically or does it happen randomly? When I say thermal excitation. So let me just quickly summarize what we discussed here. So in general, at T equal to 0 Kelvin, all the electrons of a semiconductor are in the valence band. At finite temperatures, the electrons enter the conduction band through thermal excitations. So when I use this word thermal excitation, what does it mean? Like, do the electrons move up in a systematic manner or do they move randomly? Can someone answer this question? Anyone?
Sir, randomly.
Yes. So when I say thermal excitation, the process is random excitations. So since these are random excitations, what is the next quantity I need to know? I need to know what is the probability an electron will have. Let me say this energy is Eg. So what will I have to find out? I will need to find out what is the probability an electron over here got an energy greater than Eg. Correct?
Yes, sir.
Yes. So what tells me that probability? Like what quantity tells me the probability of
The
how
Fermi
much?
function.
Yes. So I need the Fermi function for that. So as someone mentioned earlier in today's discussion, the carrier density, just use this. Carrier density is given by, in general, n is equal to integral g of e times f of e dE. Is this clear as to
Yes,
why
sir.
we wrote this? So this tells me number of, let me use a different color here so that it doesn't become a part of the formula. So this tells me number of states or rather number of available states. And this tells me probability of finding electrons. Okay, so that is all like well and good. So this is for a given material. Now, what are we here to study about, at least for the initial part of our course? We are here to study about structures that are like this: source, drain, and a channel. Correct?
Yes, sir.
Okay. So let us say I've done, the requisite mathematics, and I know the carrier density of the source, carrier density of the drain. So these two quantities I can find out using this method. Now, how do I find out how many? Now, these are connected by a channel. And now, in our course, this channel is a mesoscopic channel. So now, what happens here? So yeah, now I would like to point out over here that I will not be doing the full derivations, because I mean you're supposed to listen to the lectures to understand, I mean to learn the derivations. So I'm not going to retread the lecture content. What I'm going to do is I'm going to give you a certain, intuitive understanding, which should kind of help you with your assignment questions also. Okay, so now what is another assumption here? Like, this is a mesoscopic channel. Do we have any assumptions about the source and the drain?
Sir, they are kind of same material.
Okay. Anything more like along the lines of, is it mesoscopic? Is it macroscopic? Is it microscopic?
Sir, bulk nature, sir.
Yes. So, source. Remember, Kamal, we had this discussion once before also. Like,
Yes,
what
sir.
will
You
happen if
told
there is a.
like
Yes.
whenever we are discussing on electronic device, we have a control on channel.
Yes.
Yes, sir.
So, source and drain are treated as bulk. Okay, materials. All right. Now this is a mesoscopic channel. If it is mesoscopic, then what happens to the channel? Whatever the dimensionality of the channel is, this channel has discrete energy levels now. Is that clear?
Yes, sir.
Yes, sir.
Wonderful. So now these have discrete, what to say, like energy levels. And so what happens? So you can imagine this process like this. Essentially, so now this is a very schematic understanding of things. So on the one side, for simplicity's sake, let me say I have, you know what? Yeah, let us be. I'm just thinking of how to draw this correctly. Okay, so let me have two dotted lines. Okay, so Over here, this is the source side, this is the drain side, and this is the channel in between. Now on the source side, what I have is my conduction band, and I have the valence band. Similarly, on the drain side, I have let me try to make this a straight line as much as possible. Yeah. So I have the conduction band, and I have the valence band. So tell me this. Again, I'm not going to asking for an explanation. In silicon, do you know where the Fermi energy is?
Between conduction and valence band.
Very good. Yes. So we shall not go into the details of why that is. If you want to know that, I don't know, maybe post a question on the discussion forums and I will answer it at a later point. But it is not required for our course. Like it's not directly relevant for our course. So, in materials in general, if you have a material whose, what to say, like at 0 Kelvin, if you say that all the electrons are in the valence band and the conduction band is completely empty, then the Fermi level will be in the middle of the band gap. Like that, you can take as a rule. Okay, so I'm just going to draw a blue line to indicate that this is a special, marker, and this is kind of at the middle point. Similarly, since I mean, as one of you pointed out, uh, the materials are all kind of the same, so the Fermi level will be kind of in the same place for both of these places. So I have EFS and EFD. Now, what do I have in between? Can someone tell
Sir,
me?
in channel,
Yeah,
sir, here we will have uh, that discrete energy levels.
very good. Yes. So, like if you remember your bulk devices from maybe your bachelor's or early master's courses, if we were studying something like BJTs, I would have had my collector, base, and my emitter. And over here also, I would have drawn another conduction band and a valence band, correct?
Yes, sir.
But here, that is no longer the case. Here, what I will have are a sequence of discrete energy levels. So I will have, and let me make them as close as possible. So, I will have a set of energy levels that, actually go as high as possible, as, they may have a minimum value, but there is no maximum value. Like it can go as high as possible. However, very high energy levels are not relevant to us. So, what are these things? These things are discrete energy levels. Oops, levels. Now, tell me what will dictate the energy levels over here? Like, how do I know how many energy levels exist over here? Come on, you guys should be able to answer this question by now. Like, if I need to know how many energy levels are available at a particular energy, How do I find that out in the channel? Again, we've just discussed this today. Just now, few minutes before, in fact. We still have attendees.
Density of state.
Yeah, very good. So
DOS,
now the
density of states.
yes. So now the channel will also have a density of states. Yeah. So now I have a channel DOS. Oops. That is all. Come on. So we'll have a channel density of states. So that will tell me how many electrons are available at any how many electronic states are available at any given energy. Now, just by using your logic, tell me when conduction will occur. When will an electron start from the source, move through the channel, and go to the drain?
When there
When we
is
will
a
apply potential.
when there will be a difference of Fermi levels in the source and the drain.
Okay. Can you give me an even more fundamental uh, condition? Something that is even more basic than this. So someone said potential difference, someone said difference in Fermi
When
level.
we will connect it to a source.
Don't think about the source and the drain, think about the channel. Someone mentioned the word modes. This is what modes are. What we are about to explain right now is what modes are. The channel is no longer a material like the source or the drain. I mean, it is the same material in a chemical sense, but in a physical sense, it has a different size, it has a different structure, and there is confinement. And because of that, I have discrete energy levels, and now quantum effects will come. So, because of the quantum effects, what is the first thing that will happen? Like when I'm trying to imagine conduction.
Hello, sir. Channel is like 3D, 2D, 1D.
Yes.
Means it's 2D or 1D
It can
currently.
be anything. It can even be
Okay.
0D. Okay, by the way, if it is a 0D, then what kind of a device is it? Can you guess?
Quantum dot.
Quantum dot.
Yeah, yes. And in certain cases, not all cases, certain proposed designs of single electron transistors will also behave as a 0D channel. Okay, so for those of you who are interested in that, that is also the case. Certain cases. It is also possible to have single electron transistors with a 1D channel, if I remember correctly. Uh, Yeah, but quantum dots are the prime example for a 0D channel. So, read this statement that I'm writing. Conduction will occur if and only if there are free energy levels in the channel corresponding to the electrons in the source or drain. Is this statement making any sense?
Yes, sir.
So let me, make, like, right now I drew too many lines here. Let me make life slightly more complicated. Let me say this is a 1D channel that has energy distribution as we have discussed very many times right now. It will have energies of E naught, 4 E naught, 9 E naught, and so on and so forth. So I will have maybe, maybe E naught is around the valence band. So 4 E naught will maybe, be somewhere over here. And let me get rid of this arrow mark. You know what? Let me do this nomenclature in the bottom so that it is not interfering, and then make this black. So let me call this the source. Oops, the source, the drain, and the channel. Okay, so over here, and now I have, say, increasing energy levels at E naught, 4 E naught, and let me, just erase this side to make some more room. Okay, so I have E naught, 4 E naught, 9 E naught, and so on and so forth. So this is some, hypothetical 1D channel. So in a 1D channel, this is how my energy levels will be, correct? Something like this.
Yes, sir.
Now, if my channel already has 2 electrons here and 2 electrons here, then when will conduction occur? First, I need to take an electron from here to the 9 E naught level. And then, if from this point I need to remove that energy and send it down to the conduction band of the drain. Is that clear? Like, do you understand this mechanism?
No, sir.
See, essentially, now these are filled states. Okay, imagine. Now, this is just an example. Okay, so the channel already has what to say, like 2 electrons in the E naught and the 4 E naught, and there is a reason why I drew the bottom of the like the E naught level in the band gap. So E naught and 4 E naught are kind of in the band gap. So there are no energy levels corresponding to these energies in my source or drain. It is in the gap. Is that clear?
Yes, sir.
So if a mobile electron, which is in my conduction band, has to go from the source side to the drain side, then I at least have to jump to the 90 knot level, jump up and jump down. Is that clear?
Okay, sir.
Everyone, like, is that part clear? Like, so that is how it will happen. First, it will go up here, gain energy, and then go down here and lose energy.
So
Yes,
can
That,
sir.
you,
uh-huh.
so can you just repeat it briefly? So,
Yes. So see, the channel only has discrete energy levels because of confinement. Over here, the energy values are continuous. Like below the valence band, there is a continuous range of energies. Above the conduction band, there is a continuous range of energies. The energies in between are not allowed. Similarly for the drain side. Now, I am having a hypothetical 1D channel where, let me say, the first two energy levels are somehow aligned in the middle of the band gap. Okay, they are somewhere in the middle, like somewhere in the band gap, not in the middle of the band gap. They are in the band gap. So there are no available energy states in the source and the drain. Okay, like at this point there are no drain energy levels. At this point there are no source energy levels. So these four electrons cannot move. They are stuck here. They will be in the channel only. So in a sense, these four electrons are kind of the stored electrons. Like they cannot move. Now, mobile electrons are present. Like right now, I'm only talking about electron conduction. We are not talking about holes yet. Okay, let us just consider electrons. So, for a mobile electron from the conduction band on the source side to go to the conduction band on the drain side, the only available method is to take the first unoccupied energy level. In this case, in this particular case, I'm not saying this will always be the case. In this example that we are considering, the 9E0 state is empty. So first an electron will have to jump here, sit in this energy. So whatever this energy gap is, that energy has to be supplied, and then whatever this energy gap is, that energy will be emitted and it will jump down. So an electron will start from here, it will go into the channel and then lose energy and come into the drain. Is that clear?
Yes, sir.
So this
Yes, sir.
is the conduction mechanism for a mesoscopic channel. This is how the quantum mechanical conduction takes place, because now it is no longer a question of electrons moving in a straight line and colliding with each other. So the concept of mean free path, that you mentioned, where do we consider that? We consider that when we have electrons moving randomly in a solid and they are able to collide with each other and so on and so forth. But here no such thing happens, because this is a quantum channel. There are discrete energy levels, and in each energy level only two electrons can exist. Why? Because Pauli's exclusion principle. Okay, so what happens is, like, this is how conduction happens. The electron jumps, or it can also maybe lose energy. Like if let us say the 4E0 level was empty, then initially the electron will have to lose energy and go to the 4E0, and then gain energy and go to the conduction band on the drain side. Okay, I'm not saying it always has to gain and lose energy. It can also lose and gain energy depending on the available energy levels. Is that clear?
Yes, sir.
Yes, sir.
Yes. So this is how conduction occurs. So this is essentially the idea that you will see. Like, I mean, there will be detailed derivations for how this conduction happens. Okay. Now, yeah, the last part. So we are finishing today's session. So first concept, the number of, now do you remember the number of energy states available from E to E plus dE is the density of states. Now number of energy states available for conduction in the range E to E plus dE, E plus dE. Let me just put a small partition here. Now this quantity is what we call the modes. So modes are denoted by M of E. And in this case, the quantity will be M of E dE. Okay. So over here, in the 9e naught energy range, there is only one energy level available. Because what is the next energy state in the channel? It is 16e naught. Okay, so around 9e naught, there is only one state available. Between say 10e naught and 12e naught, how many energy states are available for conduction? In this case, can someone tell me? Between 10e naught and 12e naught? Anyone? Okay, that was probably a dog barking. Unfortunately, I do not understand what dogs say. Did you get my question?
No, sir.
Ah, so, like what I'm saying is, this energy level has energy of 9e naught. Is that clear?
Yes, sir.
So, what I'm asking is, in the energy range 10e naught to 12e naught, for this particular kind of a channel, are there any available energy levels for conduction?
No, sir.
Very good. Yeah, correct. You're right. Because what is the next available energy level? 16 E naught.
16 E naught.
Exactly. So between 10 to 12, there is nothing. Therefore, in that case, M of E, the modes function, will give me an answer 0. So you will see what the derivation of the modes are. And since the modes is directly connected to the number of the energy states in the channel, which is described by the channel density of states, of course, the modes will also be a function of the density of states. And therefore, you will see what happens in the case of a 1D channel, 2D channel, 3D channel, what kind of an energy dependence the what is it like modes will have in the case of the density of states. So the last thing we are going to discuss is the chemical potential. Like, why do I call it chemical potential? Okay, so as some of you have correctly mentioned, in order to like facilitate conduction, like generally in a say in a macroscopic semiconductor device, let us say in a bipolar junction transistor, or a macroscopic a bulk MOSFET, or a bulk MOS device, metal oxide semiconductor device, a MOS capacitor. What do we no, MOS capacitor is just a sandwich. A two terminal metal oxide semiconductor device, something like that. So essentially, what we need to do to what to say like cause a flow of electrons is to cause a change in the Fermi level. Correct?
Yes, sir.
Yes,
Uh,
sir.
so so the Fermi levels have to be like kind of moved above or below. Then tell me this: if for conduction the Fermi level has to be moved above or below, then in equilibrium, what happens to the Fermi levels?
Sir, source and drain region align.
They are
Fermi level.
same.
Yes, exactly, correct. So in equilibrium, the Fermi levels are aligned. Okay. So this is something we observe in macroscopic devices. You will find out in the lectures that even for mesoscopic devices, this is true. However, in the case of macroscopic devices, we will find that the Fermi level of the source, the drain, and the channel are all aligned. But in this case, we will find out that only the source and the drain Fermi levels are aligned, because technically there is no Fermi level for the channel, because it is a small system which has finitely many electrons. Like statistics can be done only when there are a large number of electrons. Since the channel is small, the number of electrons in the channel is very less compared to the number of electrons in the source or the drain. So the concept of Fermi level is not very strongly defined. It exists, but not in the sense that we understand so far. Maybe at a later point in the course we may talk about it, but again, it is not of direct relevance. So the source and the drain Fermi levels at equilibrium are equal. So let me write it over here itself. at oops uh, at equilibrium, EFS is equal to EFD. Okay, so this is true even for mesoscopic devices. Again, this derivation is found in the lectures. I'm not doing these derivations like over here. If you have any doubts, next week maybe tell me. I will walk you through the derivation again. So now finally, what is the chemical potential? So let me say, initially I choose two different materials, okay, rather than the same material. Let me say my source and drain are of slightly different nature, such that the Fermi levels are not aligned. Now, if I connect this source and drain through a channel, what will happen? Can someone tell me? Hello. Yeah, I mean, with this, I think the presentation part for today's lecture is, I mean, today's discussion session is over. So I will just,
Okay, sir, one question, sir.
yes, 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 please, please, please ask.
Yeah, sir, actually, in the DOS summary, there is a plot of G, E, and E.
Yes,
Yes, sir, where sir told about like for 3D, 2D.
yes,
So, sir, for suppose for 3D at E equal to EC,
yes,
so he told like there is the probability of less electron in the LUMO level, and when we go to the high, then the conduction electrons are higher.
yes.
So, is there any like what means what is the effect of that like in the device, nanoscale devices?
Nanoscale devices, the more it essentially means that the more energy you are willing to supply, probably you will have more modes for conduction. Probably.
Yes, sir.
Like when you come to the modes derivation, you will understand. Like again, I don't want to exactly mention that because some of those answers are answers to your assignment questions. So I don't want to
Okay, sir.
exactly
Okay.
give you
Okay.
those answers. Okay.
Understand.
All right. So go through the lectures. You will see that there is a connection. Yes, as you can see in a 3D case, things seem to increase as my energy is increasing.
Yes, sir.
So that implies that if I am willing to supply that energy, then maybe I will get more channels. And in maybe the 2D case, maybe no matter how much energy I supply, maybe I will not get more modes. Maybe in the 1D case, something else happens. Okay, so that variation will come as a result of the density of states. Okay,
Okay,
so
sir. Okay. Yeah.
yeah, coming back to the last point that I was mentioning, uh, what happens when the Fermi levels are initially misaligned and I connect the source and the drain whose Fermi levels don't match with a channel? What will happen? Bulk channel, mesoscopic channel, whatever. What will happen initially? Come on, you guys should be able to answer this.
Conduction.
Yes. Some electrons will move from the source to the drain or
Mm.
from the drain to the source, depending on the position of the Fermi level, in order to balance the Fermi level, in order to bring about equilibrium.
Yes, sir.
Okay. Now, how did that conduction happen? It happened because of the difference in the Fermi level. So, in
Mm.
that case, for that small current, the difference in the Fermi level itself acts as a potential.
Okay,
And
sir.
that is why the Fermi level is called the chemical potential. The
What's the
chemical nature
last
of,
point?
like, the little bit of conduction that will happen for the Fermi levels to balance out is happening because of the difference in the Fermi levels, because of the difference in EF. So
Okay, sir.
that conduction is also has to be caused, like for every current, I can define a potential, right?
Yes.
So
Yes,
that
sir.
potential in this case has been defined by the difference in the Fermi level itself. So the difference in the Fermi level is an intrinsic, inherent potential that caused the conduction until that potential value went to zero, until the Fermi levels matched. So because of that reason, the Fermi level is also known as the chemical potential. And you will find out later, like, I mean, you already know this, that whenever I apply any kind of a potential in a semiconducting device, conduction always happens because there is a change in the Fermi level. Like whenever there is a flow
Yes,
of
sir. Right.
carriers, electrons or holes, the Fermi levels will be misaligned. So the potential and what will be the difference between the Fermi levels? It will be Q times the applied voltage.
Yes, sir.
Yes, sir.
Like,
Yes,
if you
sir.
remember your old semiconductor devices theory, the same thing you will see also becomes true here, despite the fact that we have mesoscopic channels or microscopic channels and discrete levels. That particular relation will still hold because the source and the drain are still bulk. So when I apply a potential difference between the source and the drain, uh, the shift in the Fermi level is reflected using the potential difference. So since the Fermi level is connected to the applied potential difference and it is a natural chemical property of the material itself, the Fermi level is also referred to as the chemical potential. Okay. So that is one reason we can give for calling it a chemical potential. There is another statistical mechanical reason. I'm not going into it because it is not required. Okay. So I think with that we can end today's session.
Yes, sir.
Once
Yes,
again,
sir.
Yes,
I
sir.
thank you all for joining me, and and thank you furthermore for sitting for just over 2 hours and putting up with this discussion. I hope the stuff discussed was beneficial to you, and it helps you in solving your assignments and appreciating the contents of our course. And we will meet again next week, same time. Thank you.
Thank you, sir.
Thank you, sir.
Thank you.